Welcome everyone. This is the recording for September 28th, and we are starting in on section 209. This is the first day. We'll be here for a few days, and we're going to start again, I guess, continue to talk about electron orbitals. So let me make this into a full screen. And so over here, this would have been our warm-up. If I read over here on the left-hand side, it says we're going to continue to think about this hotel room. It's going to help us think about the electrons. And we have this set of bulleted rules. So only 2 people are allowed to stay in each room of the hotel. An entire floor must be full before someone or people can move to the next floor. And assume there's only 1 room per floor. Okay, so we have a really skinny hotel. So following these 3 sets of rules, how many floors will be used if 9 people check into the hotel, and where is that 9th person? And so if there's only 1 room on each floor and 2 people per room, I would have 2 on the first floor, another 2 on the second floor, another 2 on the third floor. So we have 2, 4, 6, 8. And then the 9th person would go up to the 5th floor. And so we would use 5 floors, and the 9th person would be on the 5th floor. The idea being is when we start talking about what's called electron configurations and how the electrons fill the orbitals on the outside of the atom, we're going to get a set of similar rules that the electrons follow every single time in order to fill the orbitals. So anyway, say again in section 209, our question is, how do I fill in an Aufbau diagram, or basically, how do I fill electron orbitals? And so we have 2 goals for today. The third one I think I'm going to save for when I'm with you. But the first one here is, can we explain what Schrodinger's model of the atom is? How does it look different than Bohr's? Can we interpret what's called an Aufbau diagram? And be able to describe the electron's energy and position around the nucleus based on these Aufbau diagrams. And then finally, the bottom one, we'll start actually writing configurations, which, like I said, I may save for when we're back together. So this is where we ended yesterday. We have Bohr's model of the atom. Let's see if I could scoosh this down just a little. So we have Bohr's model of atom, which is sometimes called the solar system model because it looks very much like our solar system. However, we know now that this is not really what the electron orbitals look like, and we have a more complex structure, and we're going to see that with Schrodinger. However, this model is not going to go away. So we're still going to use the Bohr model, and on the right-hand side it says why. So it makes it easy to draw, right? I could draw a Bohr model pretty easily. I could see all of the electrons. I could see all of the energy levels. I could easily count up the number of valence electrons, all things that are not easy to do in the Schrodinger model. And so we'll still see the Bohr model from time to time. We'll use it maybe to answer some questions, but we know now, cliffhanger because my slides aren't moving. We know now that the story has moved on to Schrodinger, which is a more complex structure. So that covers everything we see here in the story of our atom. Here's the Bohr model and the Schrodinger model side by side. So the big difference is the shape of those orbitals. So you can see over on the right-hand side, there are still some circles, but there's also kind of looking like petal kind of things for the electrons as well. If you read around those black lines, you can see there's a 2s orbital, there's a 2p orbital, there's a 3s orbital, a 1s orbital, and there's more. There's actually d orbitals and f orbitals as well. So you can see that the orbitals are all named by a number and a letter. And we'll eventually get an exponent as well to tell us how many electrons are on that orbital. So more complex structure, Schrodinger's model, it's called the quantum atom. And so up here, what is the quantum atom? Over at the top, it says a theory in physics based on the principle that matter and energy behave both as particles and as waves. According to the theory, matter and energy are composed of tiny units of electromagnetic energy called quanta, which is where the name quantum comes from. So the quantum atom. Again, very specific more complex orbitals, and we're looking at the way electrons travel as both particles and waves. And so it's not something you have to really memorize, but to just know where that name comes from, and it is from Schrodinger as well. So the quantum atom from Schrodinger. He said electrons are organized into orbitals that are more complex and more shapely than Bohr's solar system model. And so down here, we see the beginnings of what's called an Aufbau diagram, and we see some pictures of orbitals, but I'm going to flip to the next slide, which has them blown up so we can take a closer look. So in this slide here, I know when we were in class one day, I think I mentioned the name Schrodinger, and everyone started talking about Schrodinger's cat, and that is the same guy. So on the left-hand side, I thought I would put it up there. The idea behind Schrodinger's cat is that you don't know if the cat's dead or alive. So theoretically, both could be true at the same time, right? You're not sure what the cat is, dead or alive, until you open the box. From that stems this idea of the Heisenberg uncertainty principle, which is not something that, again, you would have to memorize or know, but I thought since we were talking about Schrodinger's cat, I might as well put this up here as well. Basically, we don't know if the cat's dead or alive, right, inside the box. Same thing over here with an electron. So we can't figure out the velocity and position of an electron at the same time. If we try to find out one, we mess up the other, sort of say. And so that idea of Schrodinger's cat moving into this idea behind electrons, that's where it comes from. So anyway, that's just FYI for your information. You could read through it if you'd like. But here's a close-up look at the shapes that the electrons travel on and how we name them. So we have 4 shapes or 4 different paths that the orbitals travel on: S, P, D, and F. So I have the F's on another slide. But we're looking at the first 3 here. So I made up words to match the letters so that we can help remember. So S for sphere, and that's the top one in red. So some electrons do travel in circles, in spheres. P I called peanut because it kind of looks like an old-time peanut that you would crack open, right? And so those are the green ones. And there's 3 different kinds of peanuts, sort of say, because it can travel on 3 different axes. So we have the x-axis, the y-axis, the z-axis. So 3 different p orbitals depending on orientation. Whereas with the sphere, there's only one orientation for a sphere, right? It doesn't matter where you are, it's the same circular path. And then finally at the bottom is the d orbitals. I've named them. Now again, these are not technical names. It's just me making up a name so that we could remember them. But I call them double peanuts just so I can match the d. But it kind of looks like 2 of the peanuts together. So the electron is traveling on that path. So all 4 of those corners it's hitting. And you could see that there's 5 different kinds of d orbitals based on orientation on the axes. And also because of what the electrons do when they're that close together, you could see that last picture there. It's a little bit different because the electrons kind of fuse, sort of say, and end up a little bit different. But those are the 3 basic letters, the ones that we're going to see the most of. S and P being the most popular, sort of say, for this class, and some D's as well. But we named the paths on shape. So the more complicated the shape, the more energy it takes to travel. So the sphere would be the least amount of energy. The F's that we're going to look at are going to be the most amount of energy. And so here's a look at the F orbitals. What I also have at the bottom there is the periodic table. And so amongst all the other things that we're going to learn about the periodic table, it's also separated by orbital shape. And I have them marked there. So the s orbitals, those elements end in an s orbital. Their electron ends in an s orbital, just like the warm-up, the person ended on the 5th floor, right? And so those 2 first columns are s block, we call them. In the middle, we have the d block. On the right-hand side, we have the p block. So these are all elements that end in that shaped orbital. The F's are at the bottom. So those are the bottom 2 rows. And because we hardly ever touch or learn about, not learn, but we don't often use those elements at the bottom. They're rare. A lot of them are man-made. They're not found in nature. And that's where we end in those F orbitals. And you could see from the pictures on the right that they're very complicated shapes. And so we don't often talk about those f orbitals or try to draw them or look at them, but they're there. And there's 7 different kinds of f orbitals, and you can see what they look like on the right-hand side. So anyway, we have 4 orbitals, and they increase by energy depending on how complicated the shape. So this would be your first question. I'm going to just pause as I read them and then give you the answers. But which of the following is a picture of a d orbital? Right, so I use D for double peanut. And in this case, that would be the blue ones, letter C. Let me see if I get out of here. I could just box it for you. So the answer is letter C. Right. Let's look at the next one. What we have here on the bottom right corner, mixed up with my right and left there for a second, is what's called an off-bar diagram. And so an off-bar diagram mirrors what you see on the left-hand side is the pictures of those orbitals. And so we don't want to have to draw those shapes all the time and the X, Y, Z axes and so forth. And so what we have is a set of boxes to represent those orbitals. So you see the first one is an s orbital. There's only one box because there's only one kind of s orbital, right? It doesn't matter which direction you're in. We have a whole column of s orbitals. So you can see every energy level, every floor has an s orbital. The numbers in front correspond to the energy level. And so this first box here is on the first floor of your hotel, the first energy level, the lowest energy, right? Because it doesn't take a lot to walk into the hotel and be on the first floor. And so the lowest energy, and it's in the shape of an S. So it's a spherical shape. So that's my first energy level, my first orbital. Then I move to the second floor. There's 2 kinds of orbitals on the second floor. I have s orbitals and I have p orbitals. And so this is what I was talking about yesterday. Even though they're both on the same energy level, the s's have less energy than the p orbitals. So the more complicated the shape, the more energy it takes to travel. And so I have 1 box for the s orbital, but I have 3 joined boxes for the p orbitals because there's 3 kinds of p orbitals, right? X, Y, Z. And it doesn't matter which direction it's going in, which axes it's traveling on, they would all have the same energy because they're all p orbitals on the second floor. And so that's why those boxes are connected. So when the boxes are connected, that means the electrons in those boxes, the electrons in those rooms are going to have the same amount of energy. Then I move to the third floor. I have S's, I have P's, and now I have d orbitals as well. And there's 5 boxes connected together because there's 5 different kinds of d orbitals, right? And again, they all have the same energy. That's why we show them connected. If we were to show the f orbitals, they would start on the 4th floor. So we would have s's, p's, d's, and then the f's would be alongside of that. But again, we hardly look at those, so we're going to stop here for now. As I'm going to flip to the next slide because I think it's a good picture. But actually, before I do, again, if we look up here at the Bohr model, we count the orbitals 1, 2, 3, closest to the nucleus, lowest energy, and we count away. Same thing here. So this 1 corresponds to the first energy level closest to nucleus. The 2 corresponds to the second energy level, and so forth. And so if I'm looking at this off-bar diagram, the floor with the highest energy right now is the 4th floor, right? That's as high as my off-bar diagram goes. And so until we get to a couple days from now, we'll talk about some exceptions to the rule. For now, top down, left to right is increasing energy, just like you read. So if I go to the next slide, it increases energy as you move down the off-bar diagram. So 1s, the first floor would have the lowest energy. The 4th floor in this case would have the highest. Energy also increases as you go left to right. So the s orbitals would have the lowest amount of energy, then the p's, and then the d's, and then the f's if they were there. So the more complicated the shape, the more energy it requires to travel on it. Right, so let's try 1 or 2 of these questions I have here. So again, I'll just pause, and then you can answer on your own, and I'll share the answer with you. So from these orbitals listed, which one would have the highest energy? right? So we have all S's here, so all traveling in the same shape, so that doesn't matter. But we have different numbers, right? So the one with the highest energy is going to be the one with the biggest number. So that's the 3s. Okay, let's look at the next one. Of these three orbitals this time, which one would have the highest energy? Right, so this time they're all on the third floor, so we're looking at the shape that's different. D would be the most complicated shape, so it would be the one with the highest energy. The D orbitals, I mean, not letter D is the answer. All right, last one. From these listed, which one would have the lowest energy? So the lowest energy is going to be the lowest number, which is 1. And then if there was more than 1, we would look at the shape as well, but we only have a 1 here, one of them, so it would be letter A. So letter A is on the first energy level, the first floor of the hotel, and it's an s orbital, which is the least complicated shape. So that would be the lowest energy. All right, I'd like to share one other slide with you, and then we'll wrap up for today, and we can pick it up again when I'm with you on Thursday, right? Because Wednesday is an asynchronous day. And so vocabulary. We mentioned this the other day, but I thought I would mention it again, that we have a lot of ways to name an orbital. There are several words that are interchangeable. So we have orbital, energy level, shell. And so I could call each row an energy level, or I could call each row an orbital, or I could call each row a shell, right? They're interchangeable. I highlighted energy level because that's the term I tend to use when I'm referring to a whole row. And then underneath that, if I use the term energy level, then I call each of these individual boxes orbitals. So they're on the second energy level, I have 1, 2, 3, 4 different orbitals. You can also say orbital and suborbital, or shell and subshell, or sub-energy level. So again, they're all interchangeable, and as I'm talking, if there's any confusion, I'll specify. But I tend to use energy level and orbital, so just pointing that out so we're not confused as we're all talking about the same stuff. All right, so that's it for now. The assignment then would be the first homework number 1, and then I will see you again on Thursday, and we'll pick up where we left off.